So, the next thing that I would like to, so that basically completes whatever I had to discuss as far as reciprocity and inter-reciprocity in LPTV networks was concerned in the frequency domain, right. Let us try and interpret what happens in the time domain, right. So, so, quick review of notation. Remember h of t comma tau was the response, very good, response at t due to an impulse at t minus tau, right. So, in other words, rather in pictures, this is the time of measurement, this is the time of application of the impulse, right, which is basically delta of tau, okay, and this is t minus tau, and this is tau. All right. Now, what comment can we make regard to an LPTV network? This is for a general linear time varying system, right. In an LPTV network, h of t comma tau is nothing but h of t plus T s comma tau, all right. And then of course, we have the convolution integral y of t, which is the output, right, is nothing but integral 0 to infinity h of t comma tau x of t minus tau d. Is the response at the output due to an arbitrary input. And this is again for a general LTV system, correct. In the special case of an LPTV system, because h of t comma tau is periodic with respect to T s, if you change t by that amount, this can be written as a Fourier series, right. This can be expanded as a Fourier series, and this is nothing but sigma over k h sub k of tau, because how will you do, how will you find the Fourier series coefficients? You will integrate this over one period of t, because t is the periodic variable. I mean the function is periodic in t. So, when you integrate with respect to t, t will go away. So, what will only remain is tau. So, h sub k of tau e to the j 2 pi times k f s times t, all right. So, in an LPTV system therefore, this further reduces to integral 0 to infinity sigma over k h sub k of tau x of t minus tau, right. Sorry, I will write x of t minus tau e to the j 2 pi k f s times t d tau. Correct? Because we are multiplying this with x of t minus tau. So, it does not make, I mean, I can push the x of t minus tau before, because it multiplies every term. And I can, I mean, whether adding and integrating or integrating and adding is the same thing. So, therefore, this is nothing but sigma over k integral 0 to infinity h sub k of tau x of t minus tau e to the j 2 pi k f s times t d tau. All right. Now, if you stare at this, what do you notice? The integral is with respect to tau, whereas this has got no tau in it. So, this can be moved outside the integral, and therefore, this is nothing but the sum over k e to the j 2 pi k f s times t integral h sub k of tau x of t minus tau d tau. Right. So, what does this remind you of? This is nothing but the convolution integral for an LTI system. So, what is this equation telling us? This is equation is telling us that the time in the time domain, I mean, this is nothing but the time domain equivalent of the harmonic transfer function stuff that we saw earlier. You basically take x of t, pass them through linear time invariant filters, right. So, the impulse response of this filter is h 0 of t, this is h minus k of t, this is h sub k of t. And what are we doing to the kth branch?
We are multiplying with the
Very good. So, what we are doing, the kth branch we are going to multiply the so this will give us x of t convolved, let me write this, spread it out a little bit. So, this is nothing but x of t convolved with h sub k of t, all right. So, this is x of t convolved with h sub k of t, all right. And this is you multiply this by e to the j 2 pi k f s times t, and you add them all up. All right. This is nothing but e to the minus j 2 pi k f s times t. Right. Does that make sense? So, this is x of t convolved with h sub minus k of t. Well, this block diagram must be familiar, right. This h of t is nothing but h sub k of t is nothing but the Fourier transform, inverse Fourier transform of the kth harmonic transfer function. So, that is nothing but h sub k of j 2 pi f e to the j 2 pi f t dt. Right, this is it. This is nothing but the time domain equivalent of the Zadeh expansion. So, I am going to, this is y of t, this is the time domain equivalent of the Zadeh expansion. All right. Now, something that I would like to draw your attention to. Now, let us say we excite an LPTV system with an impulse at t1. Correct? So, I am going to draw this. This is t delta of t minus t1, and let us say I am interested in measuring the output at t2. So, in other words, y of t2, all right. And so, what if I excite the system with delta of t minus t1, what would be the output of the kth? Excite the filter with an impulse, a time invariant filter with an impulse at 0, it gives you hk of t. Now, you are exciting it with an impulse at t1, because the h sub k is time invariant, you basically will get h sub k of t minus t1. Here you will get h 0 of t minus t1, here you will get h minus k of t minus t1. So, what will you get here?
It is like multiplication.
You will get h sub k of t minus t1 e to the j 2 pi kfs times t, right. So, what will y of t be?
It is like sum of all those.
Is simply the sum of all these terms. So, sum over k h sub k of t minus t1 e to the j 2 pi kfs times t, all right. So, y of t2 therefore
Summation of
is sum over all k
h sub k
h sub k of t2 minus t1, right, times e to the j 2 pi
kfs times t.
kfs times t2, all right. And because the system has to be causal, which is larger, t2 or t1?
Tt is the answer.
T2 is greater than T1, because a system is causal. So, therefore, you can only look at the response after applying an input. Now, let me show we can interpret this in a different way. So, okay. And again, this is very analogous to what we did with reciprocity. I can think of this same expression right as h sub k of minus t1 minus t2, okay, times e to the minus j 2 pi kfs times minus t2, correct. I mean, numerically these two are equal. Now, the question is, how do we interpret this, right? So, remember in this expression what was the T2, the T1 is the time at which
Yeah, observing.
in the first expression there.
That is time at which input is applied.
So, this is the excitation, right. H sub k is the response of the filter, of a time invariant filter
Of the K
excited at T1,
observed
observed at
T2.
T2, and the output of that filter is multiplied by the multiplication is at the
T2.
is at is the input multiplied or the output multiplied?
It is like out, HK filter output is multiplied.
Filter output, yeah. Multiplication factor for the filter output. Does it make sense? Okay. Now, if you want to interpret this equation, right, looking at the equation above, at what time are we exciting the filter?
Minus T2.
Yeah. So, this excitation at minus T2, right, at and remember, and this is a multiplying factor. Now, do you think that multiplication must occur at the input or at the output? First equation here, right, you can see that we are we are observing the output at T2, and this factor is dependent only on T2. So, therefore, the multiplication is occurring
T2.
at the output of the filter, right. Here we are exciting at minus T2, and this factor also contains minus T2. So, what does this mean?
Multiplying at input only.
We are multiplying the, so this is multiplication factor at the filter input. Do you follow? Right? And what is this therefore? How can you interpret this?
This is the measured at the
This is, yeah, so this is measurement at
minus T1.
minus T. All right. So, how can you now if you now draw the block diagram of this, how will this look like? Just for
Impulse of
argument's sake, I am going to put the input on the right side and right, draw the output on the left side. So, x of t, right, this goes into a bunch of arms, the kth arm, whatever the filter is h sub k of t is the impulse response, correct, and what is happening to the multiplication at the output of the filter or the input of the filter? At the input of the filter. And what are we multiplying the kth arm by?
e power minus j
E to the
minus j 2
minus j 2 pi kfs times t. All right. All right. And so, this is going to be h sub 0 of t, all right, and this is going to be h sub k of t this is e to the j 2 pi
sub minus k
k h minus k, sorry. h minus k of t e to the j 2 pi
KFS times
plus kfs times correct. And what are we doing with all the outputs?
some
We are adding them up. All right, and this is let us call this y hat of t. Let us call this x hat of t and then y hat of t. Okay. So, so what is it saying? If I apply an input at t2, so an impulse at minus t2, so this is delta of t plus t2 right. Let us verify this again. So, what do you get here? This is going to be
del e power minus j 2 pi kf times t2.
if you take an impulse and multiply it by w of t, what do you get at the output?
E power j 2 pi f
Yeah,
k times fs into t2.
you get e to the plus j 2 pi kfs times t2 times
Del
delta of t plus t2. Does make sense, right? So, what comment can you make about the output of the filter here?
again that is
It will be e to the j 2 pi k f s times t 2
hk of
h k h sub k of
t plus t2.
t plus t 2, right. And so, therefore, if you evaluate this at minus t 1, correct. So, y hat of minus t 1 is going to be sum over k of h sub k of t 2 minus t 1 times e to the
j 2 pi k times
j 2 pi k times f s times
t2.
t 2, right. So, let me copy this and the earlier okay. So, you apply an impulse at,
Here at t
so impulse applied at t 1, right, measured at
t2.
measured output at t 2. This will give you this y of t 2 is exactly the same as impulse applied at
minus T2.
-T2, right, and measured the output at
Minus T1.
-T1, right, and that was y hat of -T1, and that is exactly equal to
Like y of
equal to
both are equal.
y of T2. Does it make sense? And what do you see? What is the relationship between the diagram on the left and the diagram on the right? What have we done? This is nothing but the adjoint or the inter-reciprocal network of the inter-reciprocal networks of
Original.
each other. Is this clear or it's not clear?
Clear, sir.
Okay. So, this is the original network N, right, and this is the inter-reciprocal network or the adjoint network N hat, all right. So, what is the moral of the story? So, if you take the network original network N and you apply an impulse at T1 and measure, so let us say delta of T minus T1 and VO of T2, right, and this is the adjoint network. You excite the
Output at
output port
delta P plus T2.
delta of T plus T2 and you measure
Input at minus T.
VO hat of minus T1, you get the
Same output.
same output. So, VO of T2 turns out to be VO hat of, right. So, you excite at T1, measure at T2, and for this T2 obviously must be greater than T1, correct. You will get the same output if you excite the adjoint at the output port at minus T2, all right, and measure at
Minus T.
minus T1, right, and so minus T1 is greater than minus T2. All right. So, this is the time domain interpretation of inter-reciprocity in LPTV networks. You understand? Okay, we will stop here, we will continue tomorrow.